How are we doing today? Hopefully y'all are all doing well. So today we are going to be going over our notes and starting our unit on periodic trends. Now for this, you do need to make sure you've got your notes. You need to make sure you've got something to write with, and then you will actually need a periodic table because it is the periodic trends. All right. So let's go ahead and dive on into this. So what are our periodic trends? Well, they are the trends that we find on the periodic table. Now, remember that a trend is basically just a pattern that we see. And so for this, we do need to keep in mind that our periodic table, as we're moving around on it, going down or to the right or whatever it is, we can see a pattern that is starting to form. All right. So let's take a look at this. So periodicity is, again, basically the same thing as periodic trends. It's the recurring patterns that we see on the periodic table when we're looking at and comparing our different elements on the periodic table. Okay, so when we talk about periodicity, we're talking about the periodic trends. Sometimes this lesson is actually referred to as periodicity because essentially they're the same thing. Okay, it's talking about that trend that we see with our elements on the periodic table. Now, the reason we were actually able to prove a lot of these is coming all down to Coulomb's law. And Coulomb's law is basically talking about there's this difference between charges and the sizes that we have that actually will affect the forces that are attracting one another in this. All right, so essentially we can take all the different trends that we know and we get Coulomb's law. Okay, and there's actually a formula for it. You don't really need to know it, but I am going to write it down for you. So Coulomb's law is the force equals Coulomb's constant, and then you've got Q1, which is the charge of the first element, times Q2, which is the charge of the second element, divided by the radius squared. Okay, so divided by essentially the distances between the two of them. And so Coulomb's law is basically just going to explain why these trends are occurring. All right. Now, again, you won't need to actually solve any of these. You do need to know that there is a relationship between charge and distance, though. You know, the greater the charge, the stronger the forces of attraction. The greater the distance, the weaker the forces of attraction. Okay. And that kind of, if you look at your formula, if I'm dividing by my distance, it would make sense that my force is going to be less, right? Because if I've got a greater distance, then that's going to be dividing by a larger number. Charges, same thing. If I've got a higher charge, I'm going to have higher forces. And so I'm multiplying those two numbers. If I've got a charge of 1 and a charge of 3, my total would be 3 up there, right? So it's a bigger number that I'm working with. Okay. So that's Coulomb's law. So let's take a look at kind of our general things that we can look at and know on the periodic table, the periodic trends that we have and why they occur. So energy level. So the energy level, remember on your periodic table, as I move from energy level 1, which has hydrogen and helium, to energy level 2, which has what? It's got lithium and beryllium and boron and all those, right? Carbon, all those. As we move down to those, the size gets larger. Well, that really does make sense, right? If I've got my nucleus, which has my protons and neutrons in it, I've got my first energy level, with those electrons that are orbiting it, right? Electron there, electron there. And then if I move down to my energy level 2, I've got 2 energy levels. If I move to energy level 3, I would have 3, 4, 4, and so on, right? So that would be a general trend that we can find. As we're moving down the periodic table, we're going to have more energy levels, okay? Next, nuclear charge. Now, nuclear charge is essentially based off of the number of protons in the nucleus. The greater the number of protons, the more nuclear charge you have, the more pull from the nucleus. Now, we do call... a lot of times we're referring to our nuclear charge, we'll be talking about our effective nuclear charge. But nuclear charge in general is just the charge of the protons in the nucleus, okay? And so that's going to affect how much it's pulling on those electrons that are orbiting in the electron cloud. Okay, so essentially This is the number of protons, because remember, your protons all have a charge of 1. Next, shielding effect. Now, shielding effect is something that doesn't have a huge effect on our trends, but it does have a very, very minimal, very small effect. So we do like to mention it. What do I mean by shielding effect? Well, again, if I've got my nucleus and I've got my electrons in their orbits, okay, in those different energy levels, essentially what shielding effect is saying that the pull from the nucleus on that second energy level is actually a little bit blocked right there on that first energy level, okay? Now, if I add a third energy level, what's going to happen? Well, now the pull is blocked by our first, our second, before it actually gets to that third energy level. And so shielding effect does have some effect on our electrons that pull from the nucleus, but it is a very, very small amount, okay? Last thing, effective nuclear charge. Now, this is kind of one of the big ones. So shielding effect, sorry, not shielding effect, energy levels was a big one, and effective nuclear charge is a big one. And I'm actually going to star both of those, because those are kind of the two big explanations that we have for our trends. So effective nuclear charge is, again, remember, it's going to deal with your nuclear charge. So nuclear charge is, again, the number of protons. The effective nuclear charge is the pull from the nucleus on the valence electrons. Okay, so if I've got more protons, I'm going to have more pull on just from the nucleus in general. So as I get further away, the more protons I have, the more pull or effective nuclear charge I will have on that nucleus, or on those valence electrons. Okay, now Zeph is going to be affected by the size and shielding of the atom, right? So of those energy levels, the larger the atom is, the less of pull on those valence electrons there will be, okay? Now, as we add more protons, we're going to be increasing that pull, right? And so if we increase that pull, we know that that's going to be pulling on those electrons a little bit harder. But that is something to kind of keep in mind. As we get larger, we're further away, and so it's going to be harder for those to pull on those electrons, for that nucleus to pull on those electrons, okay? I kind of like to think of our Zeph as like, if I take a magnet and I stick it to the board, it's a very weak magnet, will it stick? Yes, it will. It will stick to a whiteboard, right? One of the expo marker boards that we've got at school. So it will stick to it. Now, if I take and get that magnet a little bit further away from the board and I drop it, will it stick? Well, if it's just a little bit further away, yes, it might fall a little bit and stick. And each time, if I get a little bit further away from the board and drop it, eventually what's going to happen? Well, eventually it's just going to fall to the floor, right? It's not going to stick anymore. And so the effective nuclear charge is essentially us saying, hey, at this point, we're not going to be able to hold on to those electrons anymore, okay? It is going to be that pull on that nucleus on the valence electrons. And eventually, those electrons are going to be so far away, and there's going to be such a small nuclear charge that we're going to have very little pull on those electrons, and so they're going to be able to get away. Okay. All right, y'all. So that is the intro to your periodic trends. Let us know if you got any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.